Hi everyone. This video is going to be about applying the sine rule to solve a triangle, and this one will happen to be the ambiguous case, which seems to be the one that causes a bit of grief sometimes. So here's a question. In triangle ABC, we have the length of side A is 6 centimetres, B is 7.5, and angle at vertex A is 40 degrees. We have to calculate the remaining angles and side and sketch the possible triangles. Now I like to begin by doing a drawing. So I've set this GeoGebra worksheet up to capture. Here's our question again. Now start with our angle of 40 degrees. There it is, vertex A and the angle alpha of 40 degrees, and those two lines, those rays just go off forever. So I'm going to imagine my point B is over here somewhere, and if point B is over here, then the length along this side would be length B. So I need to measure 7.5 centimetres along here and mark a vertex. I've marked a couple of distances here from the origin. This point is 6, which is going to be my length for side A, and 7.5 here. So using where is it? It's the circles. Here it is. Using the compass tool on GeoGebra, I have to first of all select a segment. So I'll select from O to R. That gives me a circle with a radius of 7.5, and then I'll move that to be centered here, and that's just as if I had a compass with the point there and the pencil here, and that's going to be 7.5 centimeters. I'll intersect. So intersect here is under this menu. I'll intersect this ray and then select the circle. That gives me an intersection point. That's nice. I just want to show the label for that point. That is not point B. I intended point B to be down there, so I had better rename you as point C. So GeoGebra just automatically assigns a name when you make a new object, a new point. Now I don't really need the circle to be visible anymore once I've done that, so I might just untick that. I don't delete the circle, otherwise I'll lose point C, because that depends upon the intersection of the circle and the ray. Now that gives me 7.5 centimetres along here. I might draw a line segment from A to C. Now I'll show the label for that segment. It's called H. Oh dear, I pressed the wrong button then, didn't I? Oh, lost control of GeoGebra for a minute. So is my line segment still there? I'll show the label for that. Again, it's automatically labelled at just point H. I don't want that. I want to rename that. I think that would be side B. And in fact, if I check the properties of the settings there, I can show not only the name but the value as well. So that's handy. There's our side B. Now the ray, I don't really need to see that object anymore because it went off forever, of course, but I measured 7.5 and put my point C there. Now I'm ready to find vertex B. I'm imagining vertex B was down here somewhere, so that's why that was opposite. And this missing side is opposite vertex A. This will be length A of 6. So that's why I have a point here marked at 6. So I'll get my compass tool going again, and I'll first select the origin, then I'll select that point to give me a radius of 6. Now I'll center that at point C, and this is the ambiguous case happening right before our eyes. Notice that I could have a line running from here down to this point to give me point B, or I could have a line running from here down to this point to give me point B. When I intersect the circle and this ray, there are two intersection points. Either one of them could be point B. So that's very interesting. Now let's complete the diagram. What do I need? I need a line segment running from here to here. I think I'd better show the label for that. Of course it's point h, isn't it? I mean, GeoGebra just decides its own naming convention here. So I'll go on to the settings, and we won't call that h, we'll call that a, because that's what it really is, isn't it? In fact, I might call it A1 because there's more than one version of this, and I will show the name and the value. This point down here, let's see, oh, it's D. Well, no, we don't want that. We want to rename that to be point A, beg your pardon, point B1, that's vertex B, there it is. So B1, side A1, that's one possible answer. But of course, this point, if we show the label, oh, we've got point B for that one. How cute, it actually got that one right. Let's rename it anyway, and let's call that B2, the second possible answer for point B, and we'll have a line segment running from here to here. Oh, I messed up again, didn't I? There we go, line segment. Let's show the label for that one. We don't want H, we want that to be renamed, and that will be length A2, line segment A2, and I probably want to show the value for that one as well. There it is, both of them are 6 centimetres long. Now, do I need to see anything else? Do I still need to see the circle? Nope, done with that. Do I still need to see the ray running along the bottom there? Possibly not, but I will need to add in line segments for the other edges here, won't I? So that one there would be length C. Let's go to the settings here. We'll call this C1, and we will show the value. So, I didn't mean that to be a capital C, we better rename you. Edges usually have a lowercase. There it is. And we also, of course, have the possibility of a line segment just running there. It still thinks I'm talking about C1, but okay. Look, in the interest of saving a bit of time, I think this shows nicely why this is an ambiguous case. There are 2 possible answers for point B. Now let's go back to OneNote and we'll do the analysis of this using the sine rule. So we don't all, of course, have to be drawing things in GeoGebra, but I do recommend a quick sketch of what's going on. So that was vertex A, and we knew that it was 40 degrees. I'm going to imagine point B is out here somewhere, and point C, the vertex C, is up here somewhere. I would have, of course, an edge running down there. That would be edge A, which we know equals 6. We were told that B, now this would be this one here, opposite vertex B, is 7.5, and we started with our 40. Now, what will we do? Well, I think the first thing we want to do is try and find this angle down here. So using our sine rule, we have sine of the angle at vertex A over A equals the sine of the angle at vertex B over B. Now we're trying to find this angle, so it would be B over A by the sine of A equals the sine of B. Let's put our numbers in place. 7.5 over 6 by the sine of 40 degrees equals the sine of B. So let's see if we can calculate that out. What have we got? 7.5 over 6 multiplied by the sine of 40 degrees. Double check I'm on degrees, yes. I have 0.803. let's go with that. Of course, we need to take the inverse sine, or the arc sine, of 0.803. Let's see what the calculator gives us. There it is. I want the inverse sine of the previous answer, and I get 53 point, I'll round that to 5, 53.5 degrees, 53.5 degrees. Now that's not the only possible answer. Always remember, when taking the inverse of a trig ratio, there is more than one answer. So we were given an acute angle here of 53. But remember, with inverse of sine, there would be an equivalent angle here in the second quadrant, which is 180. So here we go, 180 minus 53.5 degrees. There'll be an obtuse angle as a possible answer. Where'd my calculator go? Let's go 180 minus the previous answer, 126.5. So I have possible 53.5 degrees or 126.5 degrees. Now, how do I know if they both apply? Well, they both apply. We know there was a 40-degree angle in the corner, don't we? Would it make sense to have a 53.5 degree angle? Yes, because the sum of these is less than 180. It leaves a third angle possible. What if I had the obtuse angle? The obtuse angle of 126, it was 126, wasn't it? Yeah, 126. If I had the obtuse angle, well, I've still got a 40 degree in the corner. I've still got, there it is. There's the obtuse angle of 126.5. Now, is 40 plus 126 less than 180? Yes, it is. That's why this is a possible answer. In the case, let me just take that away. I've made a little bit of a mess there, haven't I? In the case that we're looking for angle C, which is the next thing to solve the triangle, we would go, well, angle C equals 180 minus A minus B. Now A was 40, that was given, and well, if we subtracted 53.5, or in this case over here, angle C would be 180 minus 40 minus 126.5. Now, both of these are going to give a possible answer. Sometimes the second one here will give a negative answer, in which case it means there was no second solution that existed. But in this case, we will get two different triangles. That's why it's called the ambiguous case. Now, 180 minus 40, well, that's just 140. If I just press answer, then that's the 13.5. That's the second one. I did the second one first. So 13.5 degrees. And if I went back and did 140, take 53.5, I get 86.5 as this one. So here we are, 86.5 degrees. So we've now found all three angles, and we see, as GeoGebra showed us originally, we see that there are two possible answers. Now, just to be on the safe side, let's get GeoGebra to tell us the size of the angle there. It's 53.5. I think it says 53. Yep, close enough. 53.5, that's the first one we found. Let's have GeoGebra tell us the size of this angle, this obtuse angle. I'm pretty sure we know what it's going to be. It's 126.5. There we go. Now, likewise, I could check this acute angle here or this larger angle here, and it would match as well. But this video is getting a bit too long now, so the main idea that I wanted to express when solving a triangle with the sine rule, you draw your diagram, get your sine rule going. When taking the inverse of sine, there will always be an acute and an obtuse angle given. When calculating the third angle, just using the angle sum of a triangle, in this particular case, both of them were possible, so there were two different answers. Sometimes this one over here will end up being a negative number because the obtuse angle is too large, in which case that second version of the answer doesn't exist. That's enough for now. I hope you have fun solving triangles with the sine rule.